The other theorem we're going to talk about in this lesson is the mean value theorem. So what this theorem says is if f is continuous on this closed interval from a to b and differentiable on the open interval a to b, then there exists a number c, and again that's the open interval right there, such that f prime of c is equal to f of b minus f of a over b minus a. Now that might look a little bit confusing there, so let's try to break that down what it means. So verbally what that means is that the instantaneous rate of change is equal to the average rate of change. So we talked about that earlier way back in Unit 1, but instantaneous rate of change is your derivative equal to the average rate of change. You'll also notice that's our slope formula. Graphically what it says is that our tangent line is parallel to the secant line. And so all of this means at some point the instantaneous rate of change is equal to my average rate of change. And at some point my tangent line is parallel to my secant line. So over here, when we're talking about the secant line, I'm talking about the line between my endpoints. So I'm going from A to B. That's my endpoints right there. At some point in between A and B, I would have a tangent line that is parallel to my secant line. So up here is my tangent line. Here's my secant line. So somewhere there, I would have a tangent line parallel to my secant line, as long as my graph is continuous and differentiable. So if a question asks you if the MVT can be applied, what it's asking you is which of these is continuous and differentiable. And so it's going to help you to remember the shapes of these graphs. So x to the 2/3, that's the one I lovingly call the bird graph. That is not differentiable at 0. Remember, a graph that has a cusp is not differentiable. So A cannot work. It's not differentiable on this interval from -3 to 3. I should write that. Not diff at 0. For absolute value of x minus 1, that is an absolute value function shifted over right 1. It's not differentiable, at its vertex. And that vertex is at x equals 1. Think about where that absolute value is 0. And 1 is on this interval from -3 to 3, so that can't be it. X minus 2 over x minus 5. I'm not going to draw the graph. I can analyze this a little bit easier. I know there's a vertical asymptote at x equals 5. But x equals 5 is not on this interval, so I think this might be my answer. Let's go ahead and check D. I have f of x equals x minus 5 over x minus 2. That has a vertical asymptote at x equals 2. And so these vertical asymptotes are not continuous or differentiable. And 2 is on this interval from -3 to 3, so that can't be my answer. My answer must be C. All right, and number 6, it tells us that our function is continuous on 0 to 12. I'm going to highlight this. And differentiable on the open interval 0 to 12. Whenever you see those, I would underline it just because it's going to be important later on. In so many of our problems in AP Calc, we're going to be looking for those two words. Based on the graph, what are all the values of x that satisfy the conclusion of MVT applied to f on the interval 0 to 12? So first of all, when you see MVT, you automatically need to check, is it continuous? Is it differentiable? It told us that already, so we know that the mean value theorem applies. So then what we're looking for, if we have a graph, the conclusion of MVT is that the tangent line is parallel to your secant line. That was the f prime of c is equal to f of b minus f of a over b minus a. So what we want to do is highlight our secant line between our endpoints. So we're looking at the line between 0 and 12, this line right here. And then we're trying to decide where do we have tangent lines that are parallel to that secant line. And so the 2 points where I would have tangent lines parallel to that would be, I can see the line drawn here and right here. So those 2 points are at 2 and at 9. And we wouldn't necessarily know that if those lines weren't drawn there perfectly for us. We maybe could estimate that that's where those lines are, but since those points are there, we're able to answer that. And so we have here C, 2 and 9, because those are the values where the instantaneous rate of change, that's tangent slope, is equal to the average rate of change, which is the secant slope. They're phrasing it differently here, but when you're looking at a graph, it's easiest to think about secant slope and tangent slope. Notice it does not include this point here, where the secant line intersects the graph. We're looking for it to be parallel to tangent lines. So you'll often see these problems with tables of values as opposed to graphs or equations. So let's go ahead and read this. We have g, which is a differentiable function. I see the word differentiable, I'm going to highlight it or underline it. With these given values, we've got g and g prime here. Is there a number c in the closed interval, absolute value, or sorry, not absolute value, the closed interval -5 to -3, such that g prime of c equals -4, and justify our answer? Now, unlike the last two problems, it didn't tell us anything about MVT, so you might not be sure what to do. But anytime you're given a derivative like f prime or g prime is equal to a number, you should automatically be thinking about mean value theorem. And so there were two things we needed to check before we could use mean value theorem. Is your function continuous? Is your function differentiable? We have the differentiable part. But if a function is differentiable, that means it's also continuous. We know that, but we need to state it. So we're going to say, since g is differentiable, it is also continuous. Now, if it gives a certain interval that it's differentiable on, you want to include that. But otherwise, if we just say it's differentiable, that means it's differentiable for all real numbers. Okay, so that means the mean value theorem applies. So what we want to check next is we're going to use this interval, -5 to -3. We're going to try to find the average rate of change on that interval. So we're going to do g of -3 minus g of -5 over -3 minus -5. Now I can use the table of values to find that out. So what I'm looking for here is g of -3, which is 2. G of -5 is 10 over -3 plus 5, that's 2. So I have -8 over 2, and I get -4. Now, we may or may not have to do more work after this. We're going to check, does this -4 match up with the value we were looking for? It does. And so then we can go ahead with our conclusion. So we can say, therefore, by MVT, there must be a place where my derivative is equal to this average rate of change. So if my function is differentiable and continuous, there is a place where this average rate of change is equal to my derivative, the g prime. So that's what I'm going to say. But what you can do is just basically repeat the language in this problem. Therefore, by MVT, there is a number c in the closed interval -5 to -3 such that g prime of c is equal to -4. And that's it. Now you might have tried to solve this problem with intermediate value theorem by looking at g prime and seeing is there a place where I would have to be -4. So I go -3 to -1 to 4 to 1 to -2 -3. I wouldn't necessarily have to be -4 there. So I couldn't use intermediate value theorem in this case. If this last one had been like -5, then maybe I could say, oh, well, -4 is between those, so I know my derivative is -4 somewhere. But in this case, we would have to use mean value theorem, so we're actually looking at the g values. Okay, number 8, we have the height of a tree at time t as given by a twice differentiable function. That means I can find the second derivative. H, where h is measured in meters and t is measured in years. Here are some values of h. Explain why there must be at least one time t for t between 2 and 10 such that h prime of t equals 2. So once again, I'm seeing that derivative equal to a number, so I know I need to use MVT. So first of all, I know my function is differentiable. It doesn't tell me anything about it being continuous. So I need to state, since h is differentiable, it is also continuous. So the next thing I want to do is try to find the average rate of change on the interval that it gives me. So h of 10 minus h of 2 over 10 minus 2. So 10 is 15, and 2 is 1.5 over 8, and so I get 13.5 over 8. That, I don't know exactly what that is, but I know it's not equal to 2. That doesn't mean that mean value theorem doesn't apply just because I use that interval and it's not equal to 2. I know mean value theorem applies because my function h was differentiable, so it was also continuous. So what that means is I need to figure out another interval where my average rate of change is 2. So you just kind of have to spot check. You have to give at least one interval. There might be more than one answer. And so what you're going to do is just look at your change in y's. So 2 minus 1.5 is 0.5 over my change in x, 1. That's not going to work. That's just 0.5. My change between 2 and 6 is 4. And my change between 3 and 5 is 2. So my change in y over change in x, 4 over 2, that does work out for 2. Okay, so if I look at the change in y over the change in x, I do get 2. So let's try that interval instead. H of 6 minus, or sorry, not h of 6, h of 5, my y value is 6, minus h of 3 over 5 minus 3 equals 6 minus 2 over 2, which is 4 over 2, which is 2. And so that does check out with the value we were given. So we can say, therefore, by MVT, there must be, and I'm going to repeat this language, there must be at least one time t for t between 2 and 10. And you could even say between 3 and 5. I know it would have to be there, such that h prime of t equals 2. So you do have to reinforce that conclusion there. Okay, and our last problem, we have this graph of f of x. It asks us to plot a line segment connecting the points where x equals 0 and x equals 3, and then determine all the values of c which satisfy the conclusion of the mean value theorem. So let's start. We're going to plot a line segment connecting the points on f where x equals 0 and x equals 3. So I'm going to sketch a line there. That's my secant line, remember. And what mean value theorem says is if I want to satisfy the conclusion of the mean value theorem, I'm looking for a line that's parallel to that line. So hard to tell exactly. That's not a very good job. I should do a better job than that. I'll try one more time, but otherwise you'll just have to kind of pretend. That's a little bit better. Let's just pretend it's intersecting the graph. Right there-ish. If I want a tangent that's parallel to that secant line, it's probably between 1 and 2. But it's not easy for me to tell exactly where it is on this graph. Some of them I might be able to tell right away. This one I can't tell exactly where it is. But I know it would be somewhere in there. So let's go ahead and go through our justification for a mean value theorem. So first of all, my equation is given to me. That's a polynomial, so I automatically know that it's continuous and differentiable. So f is continuous and differentiable since f is a polynomial. I'm just abbreviating here. You should write all that out. Okay, so what I want to check then is let's do f of 0 and f of 3. Try not to rely on the graph too much because it might be hard to tell, and pay attention that we're using an interval of -10 there on our tick marks. But if I plug in 0 to my function, I get 0. If I plug in 3, so 3 cubed plus 2 times 3 squared minus 19 times 3, I get -12. So let's go ahead and calculate our average rate of change. F of 3 minus f of 0 over 3 minus 0 is -12 minus 0 over 3 minus 0, and so I get -4. So what mean value theorem tells me, the conclusion of mean value theorem by mean value theorem, there must be a value c in the interval 0 to 3, and it is the open interval. I don't actually include those endpoints, such that f prime of c is equal to -4. Now, in some problems that would be enough, but what it's asking me for is to determine all the values of c. So now I have to figure out when is f prime equal to -4. So I'm going to take my derivative. F prime of x is 3x squared plus 4x minus 19. I'm going to set it equal to -4. And I just need to solve that equation. So I have 3x squared plus 4x. I need to add this 4 to the other side. Minus 15 equals 0. So remember, whenever you have a quadratic that you're setting equal to something, you need to move everything over to the left side or right side and set it equal to 0 and solve that. Now I can factor 3x minus 5 times x plus 3. Feel free to use grouping there if it helps you. And so I get two solutions, x equals 5/3 and x equals -3. Now you can have more than one value where this works, but if I look at my graph, I should only have one. And so you need to double check, are both of these x values in the interval 0 to 3? And this the -3 is not actually in my interval. It's just the 5/3. And so what I want to state for my final answer is that my c is just 5/3. That matches up with what I can see on the graph. 5/3 is between 1 and 2, so it makes sense. That is the place where the slope would be equal to the slope of the secant line.